Hello everyone, welcome to chapter 6. In this chapter, we will discuss chemical reactivity and the mechanisms in which chemical reactions will occur. So in the first lecture, we will talk about enthalpy, entropy, Gibbs free energy, equilibrium, kinetics, and how to read kind of energy diagrams. And in lecture 2, we will talk about nucleophiles and electrophiles, mechanisms and arrow pushing, combining the patterns of arrow pushing, drawing the curved arrows, carbocation rearrangements, and finally we'll discuss reversible and irreversible reaction arrows. So with that in, let's jump into the first topic, enthalpy. Enthalpy is the heat energy exchange between the reaction and its surroundings. So for example, if you consider this to be a system, this is the energy either going out of the system or coming into the system. We call this the enthalpy. This is the energy that is either absorbed by from the surroundings or released to the surroundings depending on the type of reaction, and this is called as enthalpy. Now, when you break a bond, it requires the system to absorb energy. When you form a bond, the system releases energy. So that's the difference here. So what happens when you have two electrons in the atomic orbital? When they bond together, so they go lower in energy. When they go lower in energy, that difference in energy is released as enthalpy. So we call this the bond enthalpy or bond formation energy. And bonds can break two ways. Either they can break homolytically or heterolytically. Homolytically, when they break it, they each take one electron. So they each take one electron each from the bond. We call these individual molecules that have one electron each radicals. We'll discuss more about this at the end of this course. And heterolytic cleavage is the most common one that you see. It's also called ionic cleavage. Ionic cleavage creates one atom gaining all the electrons, the other atom with lesser than the actual number of electrons that should be there. We call these ions. So the molecule with the deficient atoms becomes positive. The molecule that has excess atoms becomes negative. Now the energy to break the bond in homolytic cleavage, we call that the bond dissociation energy, or delta H for bond breaking corresponds to the homolytic cleavage. So enthalpy in general does not refer to the heterolytic cleavage, it actually refers to the homolytic cleavage. So remember, this is very important because ions are different from radicals. Radicals work in a different way and ions work in a different way. So these are some bond dissociation energies of different bonds. So this is the energy that you need to dissociate the bond between two hydrogens. This is the energy between hydrogen and CH3 molecule, hydrogen and an ethyl group, hydrogen and fluorine. You have 569 kilojoule per mole. The common units used are kilojoule per mole, and the practical units used are kilocalories per mole, and both of them are more commonly used there. So this is a table of all the energies. You can find more about it in the textbook in table 6.1. Now most reactions involve multiple bonds, either these multiple bonds breaking and forming. Now there are two types of reactions in general. One is called as an exothermic reaction, the other is an endothermic reaction. So in an exothermic reaction, the energy gained by the bonds formed exceeds the energy needed for the bonds to be broken. So the energy of formation is greater than the energy of broken. So this is the idea behind the difference here, which means that the products that you form here are more stable than the reactants themselves. So the energy of the products is less than the energy of the reactants. So this is how you can remember the exothermic reactions. In an endothermic reaction, so exothermic reactions, there is a net release of energy into the surroundings. In an endothermic reaction, there is a net absorption of energy from the surroundings. Here the energy of the formation is actually less than the energy of broken. So which means that the energy of the products is actually greater than the energy of the reactants themselves. So which means the products here are generally less stable. Remember that the molecules that have the lesser energy are always the ones that are more stable. So here products are more stable in an endothermic reaction. In an exothermic reaction, the reactants are more stable. So this is an energy diagram that shows you the difference here. So in an energy diagram, we see the progression of the reaction on the x-axis and the energy enthalpy on the y-axis. We start at a higher energy than comparison with the products. So this energy, once you reach a higher peak, then you come down, and the net difference between the starting energy and the ending energy is the enthalpy. And this enthalpy, if it's in the negative scale to that of the starting point, so if it's in the opposite direction to that of the starting point, we call that an exothermic reaction. If you take an endothermic reaction, the initial energy of the reactants is generally less than that of the products themselves, which means that the products here have higher energy than the reactants, and delta H here is positive. We can call this an endothermic reaction. So in an exothermic reaction, delta H here, the standard enthalpy is greater than 0, standard enthalpy is less than 0. In an endothermic reaction, the standard enthalpy is greater than 0. So here products have lower energy, energy is released as heat, and delta H is negative, and because delta H is negative, it's being released into the surroundings. The temperature will increase in the surroundings. Temperature of the surroundings will be increasing. Here the temperature of the surroundings will actually decrease. So this is the reaction that we generally see. And we use the sign plus or minus of delta H to indicate whether a reaction is exothermic or endothermic. So delta H is less than 0, delta H is negative for an exothermic reaction, and delta H is positive for an endothermic reaction. And this is best expressed by the energy diagrams, and energy diagrams are the most oftenly the ones that are used to represent the kinetics and thermodynamics of a chemical reaction. Why? Because they have two axes, the potential energy on the y-axis and the reaction progression on the x-axis, so which gives us an understanding into how enthalpy can be found. So let's take an example of this. Let's take the formation of this bond here. You have CH3, CH2, CH3 and bromine. The bromine bonds with CH3, CH, Br, CH3 plus HBr. Now, if you choose from the table 6.1, and if you remember, delta H here is the difference between the bonds broken minus the bonds formed. So the energy of the bonds broken, what are the bonds that are breaking? One bond that we are breaking here is carbon hydrogen, which is 397, and we have to break bromine bond as well, which is 193. And bonds that are forming here is we form the carbon bromine bond and the hydrogen bromine bond. Now when you add up the bonds broken and they add up the bonds formed and subtract the difference between those two, you get negative 63 kilojoule. Now delta H here is negative 63 kilojoule per mole. Notice that here it is negative, which means that this is an exothermic reaction. So this reaction here is an exothermic reaction, and this is how we can see which reactions are exothermic and which reactions are endothermic. So pause the video right here and use the table 6.1 and try to solve this problem. So pause the video right here and try these problems. So try the problems B, C and D. So use this, use the table 6.1 in the textbook and try to solve these problems. Next, let's go to the next topic, entropy. Entropy is another term that is most commonly referred to in terms of the thermodynamical quantities. So in general, both the reactions exothermic and endothermic can be spontaneous. What does the word spontaneous mean here? Is can occur by themselves without any existence of external external vibrations or external energy requirement. So this reactions occurring spontaneously means that most reactions are generally exothermic, which are generally spontaneous. But we also see reactions which can be endothermic and spontaneous. So to decide whether a reaction will occur, we need to understand whether the enthalpy is certainly there, and we have to know whether entropy is also a quantity that decides whether a reaction will occur. Now, what is entropy? Entropy is molecular disorder or the randomness of a system. So how random is the system is the degree of randomness of a system is defined as entropy, and it is actually the number of vibrational, rotational and translational states of energy of a compound and the compound's energy distribution, the freedom distribution. Now let's take an example of understanding entropy. So let's say we started with a chamber with one side being closed and one side being vacuum. When you open the valve, you notice that the side that does not have the energy, that has too many molecules, will try to migrate towards the other side. Now we do not need to know what phenomenon this is, but this is a phenomenon that will happen because the molecules want to always to try and be free. So which means they are trying to seek their freedom, and they will try to occupy as much space as they can. Now the molecules can go in number of states, and this is what is called as entropy. So as you open the valve, what you have done here is you have increased the entropy. So delta S originally, and delta S, once you open the valve, you are increasing the entropy of this particular system. Now more volume for the gas to occupy, the greater the entropy, because the greater the number of states that it can have. Now the total entropy change is determined by the process whether the process is spontaneous. Now the total entropy change is given by the sum of the system, the entropy of the system, plus the entropy change in the surroundings. For most chemical reactions, we must consider the entropy change for both the system and the surroundings. So to understand both system and the surroundings, what is the system here in a chemical reaction? The reaction itself is the system, and the solvent generally becomes the surroundings, because that is what surrounds the reactants. Now if the delta S total entropy is positive, then this process is called a spontaneous process. So if delta S total is greater than 0, we call that a spontaneous process, and if delta S total is less than 0, we call that a non-spontaneous process. So delta S of the system is significantly affected by only two factors, majorly affected by two factors. There are many other factors, but there are mainly two factors. One is their increase in the number of moles of the product than the reactant. So when there are more number of moles of the product than reactant. For example, if you see a decomposition reaction where we take one molecule and split it into 2 moles of different products, this is where entropy of the system will increase. Now the other one specific to organic chemistry is when you have a cyclic compound becoming acyclic. This is where you have freed up the system more. So when you have increased the freedom, so the system entropy will increase. So this is the idea. These are the main two factors that you have to remember. So use these principles that you learned right now and try to apply it to this. So pause the video right here and try to solve this problem. Next, let's go to Gibbs free energy. So recall that we talked about spontaneity being something that depends on total entropy change, which is the sum of the system plus the sum of the surrounding entropy. Now the surrounding entropy is something that we cannot calculate directly, so we use a function of the entropy of the system and the temperature. So the surrounding entropy change is given by negative delta H of the system by T. So from this we get a new equation of delta S of the system, total entropy of the system, which is minus delta H. So we are basically substituting this value in place of this delta of the surroundings. You get this formula here. Now multiplying temperature to everything, so multiply temperature to everything, you end up getting this equation: negative T delta S total is equal to delta H of the system minus T delta S of the system. So minus T delta S total is called as the delta G. Delta G here refers to Gibbs free energy, and delta G is a good measure of the spontaneity of a system. If delta G is less than 0, then the reaction is spontaneous. If delta G is greater than 0, then the reaction is non-spontaneous. So this is the main way we generally decide whether a reaction is spontaneous or non-spontaneous. From this we get the free energy equation, which is delta G equals delta H minus T delta S. This is one of the most important equations that you will learn, because this can help you in understanding your own body's metabolism, because in metabolism there is also the two main processes, one being the spontaneous process and one being the non-spontaneous process, where you have anabolism and catabolism. So one of them is spontaneous, the other is non-spontaneous. Delta G is a value that can determine which is spontaneous and which is non-spontaneous. Now consider the reaction that you have here. This reaction where you have a cyclic product, so an acyclic product becoming a cyclic product, which means that the entropy of the system will actually decrease. So what happens in this reaction is that we know that as the entropy is decreasing, this is a spontaneous reaction. Now because the reaction is spontaneous, the first thing that we have to know is that delta G here should be negative. For this to be negative, we have two terms that can decide which can be negative: delta H and delta minus T delta S. So delta H, for this to become negative, which means that the second term here must be greater than the first term here. So which means that T delta S has to be greater than delta H, or we can write it this way: delta H has to be less than T delta S. So which means that here delta H should be, so it must be true that delta H is a negative value in order for delta G to be negative overall. So that's the only case where you will see that the case that the system will end up becoming negative. So minus T delta S here is a small change because temperature is not changing much, but delta S of the system is changing, where you are decreasing its entropy, which means that delta S is generally negative. So when delta S is negative, which means that delta H should be negative, only in that case will we get a negative delta G value. So in other words, the entropy of the surroundings is increasing more than the entropy of the system is increasing. So this is how we can think about this reaction. Now, just like how we decided based on enthalpy whether a reaction is exothermic or endothermic, the reactions based on delta G can also be decided. If delta G is less than 0, we call that a spontaneous process, and a spontaneous process, the other name for it is called as an exergonic process. Exergonic process is a process where it is spontaneous and its Gibbs free energy is less than 0. Now in this reaction energy diagram, we have the reaction coordinates on the x-axis and the free energy G on the y-axis. So remember the difference here. Now if the process has a positive G, so if delta G is greater than 0, we know that this is a non-spontaneous process, and because it's a non-spontaneous process, the other name for it is called as an endergonic reaction. So an endergonic reaction is a reaction that favors the reactants. An exergonic reaction favors the products. So this is the main difference between Gibbs free energy. So use the principles that you learned now. So pause the video right here and try to solve this problem. Next, let's talk about equilibrium of the system. So consider an exergonic process where delta G is negative and the reaction is spontaneous. Now here the equilibrium of the reaction will be reached eventually, and a spontaneous process means that there will be more product than the reactant. So there will be more product than the reactant. Now depending on the magnitude of the negativity of delta G, we can determine how great is the concentration of the product. So the lesser the delta G value, the more the concentration of products. So the higher the concentration of the products. So why doesn't an exorganic process react 100%? Because there will always be some reactants left. The reason mainly is because as one concentration decreases, the other concentration starts increasing. So what will happen here is that from the reactant side, when you have only A and B, you have a high amount of reactant, and the Gibbs free energy, the free energy will start to decrease and will reach its minimum value at equilibrium. The same thing happens for C plus D as well. Even though if it increases more, it will also end up becoming less, and at certain point it reaches an equilibrium at that point. This point is what decides at what point the equilibrium will be achieved. And this point, if it is more towards the product, means that more product will form. If it's towards the reactants, it means that the reactants are favored. So whichever one is more favored, the curve will be towards that side. So to determine that, we use an equilibrium constant, which you already learnt in inorganic chemistry. So an equilibrium constant here is used to show the degree to which a reaction is product or reactant favored. Now, depending on this K equivalence value, we can determine whether the reaction is towards the product or towards the reactant. Now, it is determined by the concentration of the product by the concentration of the reactants. So the other formula that we generally use is delta G equals minus RT ln K equivalent, or the equilibrium constant. Now K equivalent, delta G, delta H and delta S are all thermodynamical terms, and they are only required to relative stability of the product and reactants, but they do not determine the rate at which the reactions will be formed. Now, the higher the K equivalent value, the more the product will be favored, the more percentage of the product will be formed at equilibrium. Now, when you have a high K equivalent, which means delta G will be more negative, the more negative delta G, the higher the amount of product formation. So this is how we can determine the product formation. So use the principle now. So pause the video right here and try to solve this problem. Next, let's come to the next topic, kinetics. So equilibrium decides which side the reaction is favored. Kinetic decides how fast the reaction will occur. So recall that the negative sign of delta G tells us that the product is favored and it's a spontaneous reaction, but it does not tell us the rate at which the reaction will occur, because delta G has nothing to do with the rate of reaction. And there are some spontaneous reactions that are really fast. For example, like explosives are generally spontaneous reactions that undergo really fast, but there are some reactions that take millions of years. For example, formation of a diamond, for the slow, where you have diamond forming into graphite, this takes millions of years, even though it is also a spontaneous reaction. So for this reaction to occur, again it takes a lot of time. Now, what are the factors that determine the reaction rate or the rate of reaction? It is generally the function of the number of collisions that will occur in a given period of time, and that number of collisions are the ones that affect the rate of reaction. Now, what are the factors that affect the number of collisions that occur in a given period of time? Number one is the concentration of the reactants. Number two is the activation energy. Number three is the temperature. Number four is the geometry and sterics. Number five is the presence of catalyst. Now, the rate here is generally determined what we use, what we call the rate law. So, rate law is K times, K is the rate constant and the concentration of the reactants. Here, there is no concentration of the products that is used here. Now, the rate here depends on the rate constant and the concentration of the reactants. Now, the degree to which the change in reactant will affect the rate is known as the order of the reactant. Now, the order of a reaction is represented by X and Y, and the rate is generally given by K times concentration of the reactant to the power X and concentration of B to the power Y. So, where we have A plus B reacting to form C plus D, this is the rate law that we use. Now, depending on the value of X and Y, we call this the reaction order. And depending on the value of those reaction orders, we can classify the reactions into four types actually: zero order, first order, second order, and third order. In a first order reaction, if the concentration of the A is doubled, the rate also will undergo doubled. But if in the second order reaction, if A and B are doubled, so if A is doubled and B is doubled, the rate of the reaction will increase by 4 times. In a third order reaction, if you increase the concentration of A by 2 and the concentration of B by 2, the rate of reaction will increase by quadruple. So which means that it becomes 2 to the power 4 times times 16. So the rate will increase by 16 times. So this is the idea behind first order, second order, and a third order reactions. In a zero order reaction, remember that rate is generally written as K, which means when you multiply the concentration of A by 2, the rate will not change. So that's called as a zero order, and it's very rare, so we only use first, second, and third order reactions. Now let's look at the factors that affect the rate constant K. So because rate constant also has a specific factor that determines what value it is. The first one that determines it is the activation energy. What is the activation energy? The activation energy is the minimum energy required for the reactants to undergo the formation to reach products. So the peak starting from the reactants to the peak of the energy diagram is called as the activation energy, and this is the minimum energy that is required for the molecular collisions to result in a reaction. So it is the minimum energy that you need for the collisions to occur. Now when you increase the activation energy, you will increase the number of molecules that have higher energy. As you increase the number of molecules, which means that it also decreases the rate of reaction. Now the problem here is that the only way we can increase the rate of reaction is to lower the activation energy. So the lower the activation energy, the more the number of molecules that are able to cross the barrier. If you have a high activation energy, it means that less molecules will be able to cross that barrier to undergo the formation of the product. Next one is temperature. So one another factor that can increase the rate of reaction is by raising the temperature, which will also result in a faster reaction. So at higher temperatures, what will happen is that the molecules will have more kinetic energy. The more kinetic energy means that they have more collisions. The more collisions means that they have more reactions. So this is the progression in which we think about the rate of reaction. Next one is steric considerations. Steric considerations is where, depending on the structure, if the molecules where the reaction site is hidden, then it takes a lot of time for the reaction it can affect the rate of reaction very high, because the more hindered the substance, the less chances for it to undergo a reaction. So depending on their geometry also, there is a big consideration as well. Next one and the last one is the catalyst. Catalysts are compounds that increase the rate of reaction but do not involve in the reaction. So they just speed up the rate of reaction, but they generally are not consumed in the reaction. So what happens here is that catalyst reduces the activation energy. So catalyst's main purpose, the only purpose, is to reduce the activation energy. And it provides a new path, so a new pathway for the reaction to occur. So for the reaction to occur, it provides a new pathway, but creating what we call substrates. By creating what we call substrates, we'll discuss more about this as we go along. Now, the main purpose of providing that new pathway is to reduce the activation energy. So what happens when you add up the energy here is that, recall that both kinetics and the thermodynamics are completely different concepts. Kinetics are generally determined by the activation energy, temperature, and the rate of reaction, and thermodynamics are generally dependent on the reactants per energy, the product energy, and the difference in their energies. So there are two different things. Now consider the energy diagram that you see here, which describes two different pathways for a reaction A plus B to form either C plus D or E plus F. Now the formation of C plus D here has lower activation energy, so which means that it is generally favored. In this reaction here, A plus D B will form C plus D faster. But for A plus B to become E plus F, it is more thermodynamically favored, because the difference in energy is much easier for it to cross over to finally form the product. So remember, the difference here is that the more closer they are, the easily, so the formation of C plus D here, it's lower in energy. So the first thing is it has lower activation energy, and there is a larger net difference in energy between them. So which means that C plus D here is both kinetically and thermodynamically favored. But let's take another example where we would see a different concept. Let's say here I have A plus B forming E plus F and A plus B forming C plus D. Now kinetically, if you look at it, E plus F here is kinetically favored, but there is a larger difference in energy between A plus B and C plus D. So which means that C plus D here is thermodynamically favored. So this is the reason why we have to remember that kinetics and thermodynamics are two different genres of the same music. So think about it that way. Think of them as two different genres of the same words, but they decide, and they are completely two different things, and they do not have any commonality that can create the common product. There are chances where you have the common product, but those two are completely different things. Let's talk about the energy diagram and what type of when you have multiple paths inside the energy diagrams, what are the paths and what do we call them? So each peak, every peak inside an energy diagram, we call that a transition state. A transition state is where a molecule is deciding whether to become product or reactant. So it is not completely sure whether it has to go on one side or the other side. So transition state has a 50-50 chance of forming the product. Now there is intermediate here. Intermediates are substrates that are actual compounds. So intermediates are actual compounds and require additional energy to form products. So think of them like in a production. For example, if you think of them like candies in a chocolate store. So these are things that are not wrapped yet, but they are still in the production process. So these are formed actually, but transition states are the place where there is a 50-50 chance that any one of them can be favored. So that's the idea behind the reactions. So a transition state is a high energy state where a reaction passes through, and these are generally fleeting states. You cannot observe the compound formation at the transition state, and the transition states are energy maxima, and they generally are the ones that represent when the bonds are made and are broken. So they have two processes that are looking to happen at the same time. So that's why this is what we call a fleeting or a temporary state, and these are not observed. But an intermediate is an actual compound, and it actually forms a compound, and these are the energy minima in a diagram. So these are the minimum energy species, but these are observable, and they are an actual chemical species that exist for a period of time before they further form the final compound. Now depending on the 2 points on an energy diagram that are the close in energy should be similar in structure. So which means that the transition state will always be closer to the one that is closest. So the transition state will look more like the one that is closest to. For example, in an exothermic reaction, the transition state looks like the reactants. In an exothermic reaction, the transition state looks more like the reactants. In an endothermic reaction, the transition state looks more like the products. So it will be similar in structure to the products. In an exothermic reaction, the transition state is much similar in energy in structure to the reactants. So in an exothermic reaction, the transition state resembles the reactants. In an endothermic reaction, the transition state resembles the products, because those are the ones that are the closest in energy. We call this the Hammond postulate, and this is one way we can determine that. So use that principle here. So pause the video right here and try to solve these problems. So with this, we'll end lecture 1. In lecture 2, we will discuss the rest of the lecture. So I'll see you again in the next lecture.